Hi, I'm Keaton Blair, and today I'm going to talk about my senior design project, the Tic-tac-toe robot. This design project began as a very straightforward idea. I wanted to design and build a robot capable of playing tic-tac-toe against a human user. I chose this project because it combined my interests in mechanical and electrical engineering, as well as computer vision and artificial intelligence. I worked on this project as part of the engineering senior design class, and one of the goals of the class is that students really get to experience the whole engineering design process. So this timeline illustrates some of the major design phases of the project that we worked through. Initially, I had an idea and then created a project proposal and schedule. I spent the rest of fall semester creating the preliminary design, which incorporated a basic concept as well as some decisions about major components. This semester, I've been putting together detailed construction documents such as schematics and specifications. These will be incorporated into my final design report, which will then be presented to the engineering board at the end of the semester. My first task both semesters was to create a schedule. This allowed me to assess my progress and keep track of all the different tasks that I needed to accomplish. I then worked according to the schedules that I had created, revising them as needed throughout the semester. This diagram is from my preliminary design report, and it really outlines the rough concept as a starting point. From that starting point, I could then go on to begin to model the design using computer software. Throughout the semester, as I tested my ideas on a prototype, I was able to refine and then add to the design. The progress of this design roughly paralleled the progress of the prototype, as there were a number of ideas that I wasn't sure about until after I had physically tested them. As you can see through this progression, I was able to add more and more detail to the design throughout the semester, eventually reaching a design that felt complete. Now, constructing my prototypes really helped all of my design, including the electronics. In order to create a circuit for this project, I had to test and then fix all of my initial ideas. I learned a lot from testing every piece of design. Very often the circuit didn't work, and sometimes a component was broken, sometimes my idea was just wrong, and other times I actually wired the wrong wires together accidentally. As I worked through testing and revising iterations, I was eventually able to create a complete circuit that functioned as intended. And this allowed me to create tested, proven schematics for my final design report, which you can see here. Now, I'd worked with circuit design previously during some of my labs, but because I had never designed any mechanical systems before this project, this was the hardest part for me. I started with ideas, and then I had to assemble and test them. You can see an initial test of the X and Y translating motors here. And this one on screen now shows a test of the servo motor that's used to raise and lower the Sharpie at the appropriate times. However, not all of my tests were that successful. In fact, the vast majority of the time, something broke, got stuck, or just entirely failed to work properly. And I spent a lot of time throughout this semester working through and fixing different issues that came up. However, after enough testing, troubleshooting, and repeating, I was able to see a full test of the mechanical system that actually worked. As you can see here, the robot is mechanically ready to play tic-tac-toe. Finally, not only did I have to program the coordinated movements of each motor for the mechanics, but I also had to write code so that the camera can interpret what it was seeing. I'll walk you through the image recognition progress using an example photo. This image is a good test piece because it's tilted. There are lines such as the edge of the paper for the computer to deal with, and there's also a bit of a shadow crossing the board. So the first thing we do in order to identify what the squares are is apply an edge detection algorithm along with a bit of a blur in order to create clear edges for the tic-tac-toe board. Next, we need to identify which edges belong to the board squares and which belong to the paper or other entities. We do this through their relative positions and sizes, choosing appropriately sized regions that are next to each other. Then, fitting rectangles to each edge allows us to isolate the pixels inside each tic-tac-toe square and identify the rotation of the square so that we can straighten it. With another round of edge detection, we can identify whether or not each square has a letter in it. Then, for the ones that do, we use thresholding to remove the backgrounds, and then we feed the results into a convolutional neural network. A convolutional neural network is a classification algorithm which then identifies each square as either an X or an O. Returning to our original picture, we can now have labels for every square, and the computer can now use its knowledge of the board position to decide on the best place to make a move. And so finally, after all of that process, it's nice to see some good results. My prototype runs. It's very exciting, and it's definitely enough for me to consider it as proof of concept for the design, although it's not ready for production or really even beta testing at this point. As if my focus for the remainder of the semester is on completing my final design report, I won't continue working on the prototype for the near future. However, there are a number of things that I would have liked to do given the chance. Right now, the computer vision and motor controls are written in two separate languages, and they don't have any connections. Integrating them into a single program would be essential for further development. The image recognition is also very sensitive to lighting conditions, as several algorithms require adjustments or just fail when the light changes. I would also like to make other adjustments, such as creating a circuit board or 3D printing pieces, so that the critical components and wires in the design aren't held together with hot glue and duct tape. Thank you so much for watching, and I'd also like to thank my advisor, Chris Batson, and the rest of the engineering faculty for all of their generous help.